This lesson is on the natural log function and its derivative. Be sure that you have already looked at the section that talks about the natural log function before you do this lesson. Let's look at the derivative formula for the natural log function, and then I'll talk to you a little bit about why that derivative looks like it does. The derivative of the natural logarithmic function. If u is a differentiable function of x, then we have two parts here. The derivative with respect to x of the natural log of x equals 1 over x. X must be greater than 0. Recall that so that the log function will be defined. If you have an argument of the log function that's more complicated than just an x, in other words, u is a function of x, the derivative with respect to x of the natural log of u is 1 over u times du dx. Again, u must be greater than 0 in order that this log function be defined. So what this is saying is that the argument of the function is going to go down here in the denominator, 1 over the argument of your log function, and then if this is more than just an x, you need to take du dx. Remember, if it's an x, the derivative of x with respect to x is just a 1, and so it doesn't add anything there. I might remind you that in some textbooks, instead of writing this in the form of 1 over u du dx, they'll write it as u prime over u. In other words, since that's a 1, du dx is u prime, they'll just multiply the u prime times the 1 and write it like this. I sort of like this form right here because what it's telling you is when you're doing the derivative of a log function, the argument of the log comes down here in the denominator. The derivative of that argument goes up here in the numerator. See, that's consistent here. The argument x comes down here. The derivative of x is a 1, and that goes up there. Now, why is the derivative 1 over x? Well, I want to remind you of a couple of things that you should have already had. First of all, the natural log of x is defined to be the integral from 1 to x of 1 over t dt. You also learned that in order to take the derivative of an integral, if the lower limit is some constant and the upper limit is x, and you have some function of t in here, that this derivative is just this function evaluated at x. So if we take the derivative with respect to x of the log of x, we're taking the derivative with respect to x of this integral from 1 to x of 1 over t dt. Applying this rule, I have a constant down here, x up here, so to get this derivative, all I do is take this function right here and substitute an x for the t. So that's where we get this formula. Now, we're going to use the formula to find some derivatives. Find the derivative of y equals the natural log of 3x. Well, y prime or dy dx, I'm going to draw a fraction bar. The argument of my log function goes in the denominator. The derivative of that argument, which is 3, goes on top. You'll notice here that will reduce to 1 over x. Let's do this one. Again, I have a log function. So if I'm doing the derivative here, I'm going to draw a fraction bar. The argument goes in the denominator. So that's x cubed plus 2x down here. The derivative of this argument is 3x squared plus 2. And I just put that on top. Now, sometimes you'll be able to simplify like we did here. This one will not simplify. So we'll leave the derivative as 3x squared plus 2 over x cubed plus 2x. That's really not very difficult, is it? Just remember, if it's a natural log function, the argument of the log function goes in the denominator, the derivative of that argument goes up in the numerator, and then simplify if you can. We want to find the derivative of y equal x squared times the natural log of x. Well, don't forget all of your other derivative formulas. If you want the derivative here, you need to recognize that you have the function x squared times the function natural log x. This is a product of two functions of x. Therefore, I must use the product rule when I find the derivative. So recall the product rule says you do the first function, which is x squared, times the derivative of your second function. Since that's a log, I'll draw a fraction bar. The argument, x, goes on bottom. The derivative of the argument, which is 1, goes on top. First function, derivative of second, plus my second function is the natural log of x, times the derivative of my first function is 2x. Now don't forget, it's the log function times 2x, not this x times 2x. Let's simplify this one. X squared times 1 over x would just be an x. And then we can put this 2x in front so we don't have to use parentheses to indicate that multiplication. Our derivative is x plus 2x log x. A lot of times you will see this final answer written in a factored format like this, where they've just factored the x out. While we're here, I also want to show you some other possibilities. I don't know that they would do this, but if you remember your rules concerning logarithms, do you see what I'm doing here? Remember, if you have a coefficient in front of a log, it can move up as a power. So I could write this answer as x times 1 plus the log of x squared if I'd like. Actually, all three of these are acceptable forms of the solution for the derivative of this function. I just want to warn you, because sometimes they'll do little funny tricks like this. You may have this, and the back of the book has this, and don't just immediately assume you're wrong. Look at it and see if you can use those rules concerning logarithms to rewrite. Now, speaking of using the rules, I want to talk about that here. F of x is the natural log of the cube root of x plus 2. Now, you can write this as the natural log of x plus 2 to the 1/3 power. Now, if you don't think ahead here, if you just go immediately saying, okay, I've got a log function, so to get the derivative, I'm going to put the argument down here and take the derivative of the argument. Gee, that's chain rule, 1/3, x plus 2 to the negative 2/3 times 1. Then you have to simplify this. Let me show you an easier way. Again, thinking about your rules with logarithms, remember, if you have a power on your argument, that power can come down in front. 1/3 natural log x plus 2. This now is a constant times my function. So to get my derivative, all I really have to do is bring that constant down times the derivative of my function. Draw your fraction bar. X plus 2 would go on the bottom. The derivative of x plus 2 is 1. And so I'm going to end up with 1 over 3 times the quantity x plus 2. See how easy that is? Now this one, if you go ahead and simplify, you can move this down. You would have 1/3 over x plus 2. If you move this down to positive 2/3, add those, you get 1. And then you can multiply top and bottom by 3, and you can get there. But it's just a lot easier to move any exponent down in front using your rules for logarithms and then take the derivative. Look at this one. We want the derivative of the natural log of x squared times x cubed plus 5 to the 4th over the square root of 3x plus 4. If you don't do some work on this one before you take the derivative, it will be a very, very difficult derivative to take. Think about putting all of this in the denominator of a fraction, and then up there in the numerator taking the derivative of all this junk using product rules, quotient rules, chain rules. It would be a mess. What we want to do here is, before we take the derivative, we're going to use our rules about logarithms. Remember, if you have the log of a quotient, you can write it as the difference of two logarithms. So I can write the log of x squared times x cubed plus 5 to the 4th minus the log, and I'm going to write this as 3x plus 4 to the 1/2. The log of a quotient is the difference of the logarithms. Then here we have a product. The log of a product is the sum of the logarithms. Do you remember all those rules when you studied logarithms? So I can write that as the log of x squared plus the log of x cubed plus 5 to the 4th minus the log of 3x plus 4 to the 1/2. Now I'm still not through rewriting. Each of these has powers, which means I can bring those in front. 2 times the log of x plus 4 times the log of x cubed plus 5 minus 1/2 times the log of 3x plus 4. Now, a lot of students think because they've done all this work that they're finished. We have not taken a derivative. I want you to understand. All we have done is used our properties of logarithms to rewrite our function, to string it out as simpler logarithms. Now we're going to take the derivative. So on this first term, I have the constant 2 times the derivative of log x is 1 over x. Plus, I'm going to bring down the constant 4 times. On this second log function, draw the fraction bar. X cubed plus 5 will go in the denominator. The derivative of that, which is 3x squared, will go on top. Finally, bring down your minus 1/2 constant. You have another log function. Draw your fraction bar. 3x plus 4 goes in the denominator. The derivative of that, which is a 3, goes on top. Now, you might want to rewrite this as 2 over x. You can write this as 12x squared over x cubed plus 5 and minus 3 over 2 times the quantity 3x plus 4. Now, you have the derivative. You can leave it in this answer, in this format. If you wanted to, you could get a common denominator here and add this up and get a single term. Even if you have to do that, that's still a lot less work than trying to take the derivative of this log function in this form right up here. So learn to rewrite logarithms using your properties of logarithms first so that your argument is not so complicated. Then it's much easier to take the derivative. Find the derivative. Y equals x minus 3 squared over the square root of x squared plus 2. You might be saying, what is this doing here on the lesson on log functions? There's no logarithm. You could certainly do this by using the quotient rule. And in fact, when you study the quotient rule, you probably did something like this. Notice this denominator is the 1/2 power. So when you take the derivative of the denominator, you're going to get a negative 1/2 power. You have to have chain rule. It is a complicated derivative to take. What we're going to show you is a process that we call logarithmic differentiation. This process is one that can be used to find the derivative of a complicated function like this in a much easier way. Recall, if two things are equal, then their logarithms are equal. So what I'm going to do is write this as the natural log of y over here equals the natural log of x minus 3 squared over x squared plus 2 to the 1/2. Now, on this second side over here, I'm going to do some rewriting like we did a minute ago. I'm just going to leave that log y. This is a quotient, so I have the natural log of x minus 3 squared minus the natural log of x squared plus 2 to the 1/2. Then again, I'm going to bring the powers down. So the natural log of y will equal 2 times the natural log of x minus 3 minus 1/2 times the natural log of x squared plus 2. So I took the log on both sides, and then I've rewritten this right-hand side in a much easier format. Now, we're basically going to do this derivative implicitly. So starting over here, I have the natural log of y. Well, it's a log function, so I draw a fraction. The argument goes on the bottom. The derivative of the argument, which is y prime, goes on top. On this side, I'm going to bring the 2 down, times, draw a fraction bar. X minus 3 goes on the bottom. The derivative of that is 1, so that goes on top. Minus, bring down the 1/2. I have another log function, so draw a fraction bar. X squared plus 2 goes on the bottom. 2x, the derivative of that goes on top. Now, let's do just a little bit of simplifying here. Y prime over y equals 2 over x minus 3 minus, notice the 1/2 times the 2x, those 2's will cancel, so minus x over x squared plus 2. Now, I'm going to solve for y prime by multiplying both sides of my equation by y. Here my y's cancel. So I have y prime equals, I'm going to write the y in front, y times the quantity, 2 over x minus 3 minus x over x squared plus 2. Now I have the derivative, but I have it in sort of an implicit format where I have the x and the y mixed. So I'm going to change that. We're going to fix it. Y prime equals. Now, in place of y, look up here. Here's what y is equal to. So I can replace y with this stuff. So I'm going to put x minus 3 squared over the square root of x squared plus 2 times the quantity 2 over x minus 3 minus x over x squared plus 2. Okay? Now, you, of course, at this point have the derivative all in terms of x. And it might be sufficient to leave your answer here. But I want to show you some algebra things that you can do, which may be done as they report this answer. Let me leave this right here for now, but I am going to write this as x squared plus 2 to the 1/2 down here. Inside here, I'm going to get a common denominator of x minus 3 times x squared plus 2. Okay? Now, this fraction would be multiplied by x squared plus 2 on top and bottom. So I'd have 2 times x squared plus 2 on top, subtract. This fraction would be multiplied by x minus 3. So I'd have x times x minus 3 on top over the common denominator. Alright, I have x minus 3 squared. Down here I have x squared plus 2 to the 1/2. And simplifying this, I have 2x squared, let me just sort of write it right here, 2x squared plus 4. I have a minus x squared plus 3x. So 2x squared minus x squared is x squared. I have a plus 3x plus 4 over x minus 3 times x squared plus 2. Now, notice, this is a single fraction times a single fraction. So this x minus 3 will cancel one of those. So in the numerator, I will have 1 factor of x minus 3 times x squared plus 3x plus 4. And in the denominator, these factors are alike. So when I multiply them, I add exponents. 1 plus 1/2 is 3/2. So I can actually get my answer pretty compact down like this. Now, let's sort of review what we did. We started out with a function where it was going to be rather difficult using the quotient rule to get the derivative. So we took the log on both sides. We simplified our logarithm over here using our formulas. Then we took the derivative implicitly. We did a little simplifying. We multiplied both sides by y to get rid of this and solve for y prime. Then we replaced our y with what it was equal to originally, did some algebra in here, and finally got this simplified version of our answer. That's called logarithmic differentiation. There's not a log in the original function, but you introduce logs just to make the derivative process a little bit easier. We have a rule concerning derivatives involving absolute value when a log function is involved. That didn't print very dark. Let me darken that for you. Remember how when you find an antiderivative of a log function, how the formula actually says the antiderivative of 1 over x dx is the natural log of the absolute value of x? The reason we put absolute value signs on the argument of log functions is because those arguments have to be positive. You can't do a log of a negative or a 0. So here it's saying if u is a differentiable function of x, and u is not 0. Now, it could be negative. That means if you have the log of that u, you've got to have absolute value signs on that u. To take the derivative with respect to x of the natural log of the absolute value of u, notice it says you just do u prime over u, just like the normal formula. So basically, that absolute value sign on there doesn't matter, is what it's telling you in terms of how you find the derivative. Let's apply that. If we have y equals the natural log of the absolute value of sine x, see, the absolute value is there because the sine of x is sometimes negative, isn't it? If it becomes negative, we couldn't do the log. But if we're going to find our derivative of y with respect to x, according to that rule, we still put u in the denominator. So u is sine x. We still take the derivative of that, which is cosine x, and put it on top. You'll notice in this formula there are no absolute value signs on either u or u prime. So we just do the u sine x down here, the u prime up here. Now if you'd like to write that as cotangent x, you certainly could. Cosine x over sine x is the cotangent of x. So the derivative is the cotangent of x. Here's another one. Y equals the natural log of the absolute value of secant x plus tangent x. Again, this sometimes becomes negative, doesn't it? If we want dy dx, we're going to draw our fraction bar. We're going to put u, which is secant x plus tangent x down here. The derivative of that goes on top. Well, the derivative of secant is secant x tangent x, plus the derivative of tangent is secant squared x. Okay? Now, I notice up here I have a common factor of secant, so I'm going to factor that out. Secant x will leave tangent x plus secant x. Down here I have secant x plus tangent x. Notice that's the same thing, so I can cancel those, and my derivative will simplify to just the secant of x. We have now looked at several examples on finding the derivative of a log function, what happens if we have an absolute value on that argument of that log function, how to introduce logs to do derivatives. We're going to turn our attention now to doing some graphing. Recall that you've learned that the first derivative can be analyzed and you can determine where a function increases or decreases. The second derivative can be analyzed and you can learn where a function is concave up or down. This enables you to find maximum and minimum points and points of inflection, and using that information you can sketch graphs. A lot of times we also want to find intercepts. Well, we're going to apply those techniques to some functions involving logarithms. Find the intercepts, the relative extrema, inflections, and sketch the graph. Well, let's talk about the intercepts. To find y-intercepts, you let x equal 0, don't you? But can we let x equal 0? Notice here, x cannot be 0. In fact, the domain of this function, x must be greater than 0 because we have the log of x. X can't be negative and it can't be 0. X can't be 0. That tells me there are no y-intercepts. Okay? Now to find x-intercepts, you let y be 0. If we let y be 0, I have 0 equals x plus the natural log of x. That's going to be very difficult to solve for x. Even if you bring this x over here, that is difficult to solve. If you rewrote it, this means the exponent you put on e to give you x is this, e to the negative x equals x. That's still difficult for us to know. So as far as the x-intercept is concerned, I think there probably is one, but I'm not real sure where it is just yet. Maybe we can determine that a little bit as we get in more information about our graph. Sometimes you'll find that the intercepts are going to be a problem when you have log functions. Now, relative extrema is referring to maximums and minimums, right? And we can learn that if we analyze increasing, decreasing. All of that information comes from the first derivative of our function. So let's get the derivative of this function. Y prime, the derivative of x is 1. The derivative of log x is 1 over x. Now I'm going to get a common denominator here. 1 over 1 would be x over x. So x over x plus 1 over x gives me x plus 1 over x. It will be easy in this form to find critical values. Now, the denominator would be undefined if x is 0, but remember, my domain does not include that. This would equal 0 if x plus 1 is 0. That gives me x equals negative 1. So my only critical value is x equal negative 1. Okay? Now, since x must be greater than 0, I would have an interval from 0, no I don't. My only critical value would be -1, which is not in the domain. That's what I want to say. -1 is not in the domain, and so I end up with no critical values. In fact, look at this. If x must be greater than 0, positive plus 1 over a positive is always positive. Okay? So I am always doing what? I am always increasing. There are no maximums or minimums. Always increasing. Okay? Now, I'm going to come back to this form of my first derivative, but I'm going to write it as 1 plus x to the -1, because in this form, the second derivative will be easier. The derivative of 1 is 0. The derivative of this is a minus 1x to the -2. That can be written as -1 over x squared. Now, x squared is always positive. So I have a negative over something that's always positive. This one is always negative, which says my curve is always concave down. There are no inflections. Okay? Well, what did we learn? Well, let's see. Our curve is always increasing. It's always concave down. Always increasing, concave down. It's got to be shaped something like this. Increasing, concave down. The problem is we don't know exactly where we would cross the x-axis. Okay? Now, you can do a little bit of playing with your calculator. Notice that if I do a few little values here of x and y, if x is 1, I have 1 plus the log of 1. Well, the log of 1 is 0. Okay, so when x is 1, y is 1. If x is 2, I have 2 plus the log of 2. If you do 2 plus the log of 2 on your calculator, that's about 1.3. Since my curve is always increasing, I'm going to keep going up. I won't cross the x-axis. That way my y values are going to keep getting bigger. So let's go between 0 and 1 and see what happens. Okay? Let's use a 0.5 for x. So if y is 0.5 plus the log of 0.5, let's do that on our calculators. 0.5 plus the log of 0.5. Well, I got -0.2 if I round off. Okay, so somewhere between 0.5 and 1, I will cross the x-axis. Now, you could play with your calculator. You could use a 0.6. 0.6 plus the natural log of 0.6. That value is positive, as it turns out. I get a positive 0.1 if I round off to tenths. So that narrows it down that somewhere between 0.5 and 0.6, my graph is going to cross the x-axis. So what I'm going to do is go to my graph. I know when x is 1, y is 1. When x is 2, I'm about at 1.3. When x is 0.5, I'm down at -0.2. And 0.6, I'm barely above. So my graph is going to come along something like this. Notice it's always increasing. It's always concave down. Why am I not going across this y-axis? X must be greater than 0. So I will have an asymptote here. The y-axis will be an asymptote. This graph will look a lot like your regular log function, but adding this x just makes it go up a lot faster than just the regular log function did. Okay? Now, that one was okay, but it wasn't really interesting because it didn't have any max mins or anything. So let's take a look at another one. We want to do the same thing here. Intercepts, relative extrema inflections, and sketch our graph. This time, we have y equals the product of x squared times the natural log of x. Again, since this natural log of x is here, my domain, still, x must be greater than 0. Otherwise, that's undefined. So, as we look for these critical values and intercepts, we have to keep this in mind. Okay? So, again, x can't be 0, so we will not have a y-intercept. There's no y-intercept. Now, if we said y equals 0, that would force either x to be 0 or the log of x to be 0, wouldn't it? Because this says x squared times log x. Well, x squared equals 0 would force x to be 0, which can't happen. Can the log of x equal 0? Can that happen? Well, let's think about this. This is saying the exponent you put on e to give you x is 0. E to the 0 equals x. Well, e to the 0 is 1. So I do have an x intercept because whenever x is 1, y is 0. Okay, you can see it here. Log of 1 is 0. Okay, so 0 times 1 is 0. So I do have an x intercept this time. Now let's get the derivative and see what else we can learn. Notice I'll have to use a product rule here. This function times this function. My first function is x squared. The derivative of my second one, 1 over x. Plus my second function is the log of x times the derivative of my first one, 2x. Let's simplify. X squared times 1 over x is an x, plus 2x times the natural log of x. Now I can factor x out of this. X times 1 plus 2 log x. This is my derivative. Now to look for critical values, I want to know what's going to make this equal 0. Well, this factor would not happen because it's not in my domain. Can 1 plus 2 times the log of x equal 0? Well, let's see what that would say. If I take the 1 over here, I'd have 2 times the log of x is negative 1. The log of x then is negative 1/2. Remember, this means the exponent that goes on e to give you x is negative 1/2. E to the negative 1/2 gives me x. How much is e to the negative 1/2? Well, you can do that with your calculator using your e to the x function. So if you get your e to the x and you put in an exponent, now be careful and make sure that you notice that that's a negative 1/2. E to the negative 1/2 is about 0.6. I'm just going to round it off, approximately 0.6. 0.6 would be in my domain. So my critical value is x equal e to the negative 1/2. Okay? Now, I'm just going to go ahead right here and set up an interval. Since I have to be bigger than 0, I'm going to go from 0 to e to the negative 1/2 for one interval, and then from e to the negative 1/2 to infinity with the other. And we're going to analyze this derivative. Now, x will be positive in either of these, so this factor is positive. 1 plus 2 times the log of x. Let's pick something in this interval. That means it has to be less than 0.6. We could use, say, 0.1. If you do 1 plus 2 times the natural log of 0.1 on your calculator, you will get a negative value, which says we are decreasing. Okay? Now, if you pick a number in this interval, it just has to be larger than this 0.6. So let's say we use a 1. Well, the natural log of 1 is 0. So 1 plus 0 is a 1. That's positive. Of course, that's positive. So we're increasing here. So if we go from decreasing to increasing, what did we do? We had a relative what? Minimum at x equal e to the negative 1/2. Now we're going to get the y value that goes with that. Where do you go to get y values? You go back to the original function. So y would equal e to the negative 1/2 squared times the natural log of e to the negative 1/2. Now let's look at that. Power to a power, you multiply exponents, so e to the negative 1. Here, since this is a log, I can bring the negative 1/2 down in front, natural log e. The natural log of e is a 1. So I get negative 1/2 e to the negative 1. Negative 1/2 e to the negative 1 is my y value that goes for that minimum. Now again, remember this is approximately 0.6 right here. Let's get an approximate value for our y value so we'll know where to locate that. So if we do negative 0.5 times e to the negative 1, I'm getting about negative 0.2. So my minimum point is roughly at 0.6, negative 0.2. Okay? All right, so we know where we're increasing and decreasing, and we know where our minimum is. So we've done extrema here. Now, to get inflections, we need a second derivative, don't we? Okay, let's go back to my first derivative, and I'm going to look at it right here to get my second derivative. So the derivative of x is 1 plus. I have to do a product rule here. My first function is 2x. The derivative of the second is 1 over x. Plus my second function is log x times the derivative of the first is 2. Let's simplify. 2x times 1 over x is a 2, and then I can put this 2 in front of the log function. So I have 3 plus 2 times the natural log of x is my second derivative. Well, to get critical values for my second derivative, what makes this equal 0? Well, I'd have 2 times the natural log of x would be negative 3. So the log of x would be negative 3/2. Let's rewrite. The exponent that goes on e to give you x is negative 3/2. So x equals e to the negative 3/2. Now let's get an approximate value for that one. So let's use our calculator again. And we want to do e to the negative 3/2. That is approximately 0.2. Okay? Now, that's in our domain. So again, let's do intervals from 0 to e to the negative 3/2, from e to the negative 3/2 to infinity. This time we're going to look at this second derivative. So I need to pick something in this interval, which means it has to be less than 0.2, like maybe a 0.1. Well, let's see. If I do 3 plus 2 times the natural log of 0.1, I get a negative. That says I'm concave down. Okay? Now, if I pick something larger than 0.2, we can use a 1. The log of 1 is 0. 3 plus 0 is a 3, which is positive. I'm concave up. So what happened? I have an inflection, right? I change from concave down to up. The inflection occurs at e to the negative 3/2. Again, we're going to get the y value. This is approximately 0.2, which will help us locate. But let's get our y value. Again, where do you go? You go back to the original function, x squared log x. So I would have e to the negative 3/2 squared times the natural log of e to the negative 3/2. Power to a pair multiply, e to the negative 3. Bring this down, negative 3/2 log e. The log of e is 1. So I have negative 3/2 times e to the negative 3. Now let's get that value. So if you want to do e to the negative 3 first, or second, doesn't really matter, times negative 3/2. That is about negative 0.1. It's really 0.07, but we're going to say about negative 0.1. Okay? All right, well, let's see if we can assemble all of this information on our graph. So let's go to our graph, and I'll see if I can kind of keep some of this up here. We had an X intercept at 1, 0. That's right there. I am decreasing until I get to about 0.6 for X. So I'm going down. That point is 0.6, negative 0.2. So that is just like barely below the x-axis. I've got to decrease to that point, and then I start increasing. So I'm going to come down and then go up. Okay? I am concave down until I get to roughly 0.2, and then I change to concave up. 0.2, negative 0.1. That's way in there. You might want to use a different scale. Can you see that? So I'm concave down, and then right there I change to concave up. I'm decreasing, and then I'm increasing concave up. The question is, what's going on in between there? This is the only place I can cross the x-axis. So I can't come up as an asymptote. My function is not defined at 0. I'm assuming here that what's happening, I have an open circle at 0, 0. There's not a graph there. Let me sort of blow that up a little bit. At 0, 0, I've got an open circle. I'm decreasing and I'm concave down for a while, and then at that inflection I change to concave up, still decreasing. So I'm concave down, then concave up, decreasing. Then I start increasing concave up and go through that 1, 0 point. Okay? You might want to put that on your graphing calculator and it maybe blow that up a little bit, zoom in a little bit, and see if you can see that. That's an interesting graph, isn't it? I want to do one more graph for you. The reason I'm doing so many of these is because this is good practice not only in getting the derivatives, but also in learning to solve those equations and find those critical values. So again, we want intercepts, extrema, inflections, and sketch the graph. Well, again, since I have log x, my domain, x must be greater than 0. So we will consider nothing 0 equals 0 or negative as far as x is concerned. Well, let's see. I can't let x be 0, so there's no y-intercept. Can y be 0? Can I have a 0 over here? Well, keep in mind, if you have 0 equals the log of x over x, what if x is 1? If x equals 1, the log of 1 is 0 over 1 equals 0. So I do have an x-intercept at 1, 0. Okay? Now, let's get our derivative. Y prime. Quotient rule this time. Denominator x times derivative of numerator 1 over x minus numerator log x times derivative of denominator 1. All of this is over denominator squared. Okay, let's simplify this. X times 1 over x is 1. So I have 1 minus the log of x over x squared. Okay, if this is equal 0, then 1 minus the log of x would equal 0. 1 equals the log of x. The exponent you put on e to give you x is a 1. So my critical value is e to the 1. That's approximately how much? Do you remember the value of e? It's 2.718 roughly. So let's just say about 2.7. Okay, let's do intervals from 0 to e, from e to infinity, and let's see what's going on with this first derivative. Notice my denominator is x squared, which is always positive, no matter what x is. Okay, let's look at the numerator. If I pick something less than e, like say a 1, the log of 1 is 0. 1 minus 0 is 1, which is positive. Positive over a positive, so I'm increasing. Okay? If I pick something larger than e, like say a 3, do 1 minus the natural log of 3. That's a negative number over x squared, so we would get a negative. We're decreasing. I went from increasing to decreasing, so I have a relative maximum at the x value of e. Well, let's come back to here to get y. Y equals the log of e over e. Well, the log of e is 1, so 1 over e. That is approximately 2.7 for x, and if we do 1 divided by e, that's about 0.4. Okay? So that will give us an approximate location. Increasing to roughly this point, then decreasing. Okay? Alright, let's get our second derivative. Okay, we're going to look at this form right here. Quotient rule again, right? To get second derivative. Denominator x squared times the derivative of the numerator. 0 minus 1 over x, so negative 1 over x, minus the numerator, 1 minus log x, times the derivative of the denominator is 2x. This is all over denominator squared, which would be x to the 4th. Okay, well, let's do a little simplifying here. X squared times minus 1 over x is a negative x, isn't it? 2x times 1 is 2x, that makes it negative 2x. And then that'll change to a plus 2x log x over x to the 4th. Okay, we can add those x's together. Negative 3x plus 2x times the natural log of x over x to the 4th. Notice we can factor an x out. Negative 3 plus 2 log x over x to the fourth. Finally, we can cancel one of the x's. Negative 3 plus 2 log x over x cubed. Now, if this is going to equal 0, it would have to be the numerator. Negative 3 plus 2 log x equals 0. We have 2 log x then would equal 3. Log x would equal 3 halves. The exponent you put on e to give you x is 3 halves. So e to the 3 halves is x. Alright, so we're going to do an interval from 0 to e to the 3 halves and from e to the 3 halves to infinity. And we're going to analyze this second derivative. Okay, an approximate value for e to the 3 halves is about 4.5. Approximately 4.5 there. So we need something less than 4.5. Okay, let's just use a 1 and let's look at this. Of course, 1 cubed is 1, that's positive. Log of 1 is 0, so I'm negative over a positive is negative, so I'm concave down. Choosing something larger than 4.5, let's just use a 6. Of course, 6 cubed is positive down here. Negative 3 plus 2 times the natural log of 6 gives me a positive answer. So I have a positive over a positive is positive, I'm concave up. So I have an inflection, don't I? The inflection is going to occur at e to the 3 halves, okay? Well, let's get our y value. So y would equal the natural log of e to the 3 halves over e to the 3 halves. That is 3 halves natural log e over e to the 3 halves. That's a 1. So that's just going to end up being 3 over 2 times e to the 3 halves. Okay? Let's bring that down here. 3 over 2e to the 3 halves. Now, again, let's get proximate value so we can locate. That's about 4.5 for the x. We've already done that one. So let's do 3 halves. I'm sorry, 3 divided by the quantity, 2 times e to the 3 halves. 3 halves, of course, is 1.5. That's about 0.3 is what I'm getting. Okay? All right, well, let's see if we can assemble all of our information and get a sketch of a graph. Okay, let's start. We had an intercept, X intercept at 1, 0. So we're here. Okay? We had a relative maximum at roughly 2.7.4. 1, 2.7.4 might be right along in there. Okay? Let's see. We have an inflection at 4.5.3. 1, 2, 3, 4.5.3 is going to be just a little bit below where that maximum was, right? Okay, we're increasing until I get to this maximum point, and then we're decreasing. Okay, so we're going to be increasing to here, then decreasing. Notice on our concavity, we are concave down in the beginning. So we're increasing, concave down. We stay concave down till we get to our inflection, but we start decreasing here, so we're decreasing concave down. At this inflection, we start concave up again, but we're still decreasing. Now let's talk about this. The only x-intercept was here. I can't decrease concave up and come across the x-axis. So what must be happening is that I'm concave up, decreasing, so I'm approaching this x-axis as an asymptote. So I'm increasing concave down through my intercept to my maximum, decreasing concave down to my inflection, decreasing concave up, approaching the x-axis as an asymptote. You might be wondering why we do all that work if you've got a graphing calculator. Sometimes it's important to find those exact inflections or maximums or minimums, but mainly here we just wanted to practice these derivatives and review some concepts from those curve sketching lessons and let you see how you can construct the graph using that information. Then it's always nice to use that graphing calculator and kind of verify that what you've drawn in is correct. This completes our lesson on the natural log function and its derivative.